So, I didn't expect to give this talk. Dennis told me on the airplane I was giving this talk. But then he's supposed to help. So we'll see. I'm going to put a diagram on the board. You remember that in the previous talk, there's a big diagram of ordinary differential cohomology. So now I'll put up another diagram which will stay for the duration of the talk. And this is very fat chalk, I have to say. Let's see what happens. Okay, so I'm going to use this whole board for this diagram. And in the middle, I'll put k hat. And up here, I'll put k even. And down here, I'll put wedge BGL. And over here, I'll put H even, coefficients, complex coefficients. And over here, I'll put K odd. Of C mod Z, whatever that is. And here I'll put wedge odd modulo wedge GL. And finally over here, I'll put H odd with complex coefficients. And then we'll put a lot of arrows.
You're going to put the zero?
I'm going to put the zeros. Up here is a 0. Down here there's a 0. See, that's why I need the whole board. Down here there's a 0. And up here, there's a 0, and this goes here, and this goes here, and then I'll label. Some of these things will look familiar, some of them won't. That's Chish, that's a delta, this is a Bachstein, this is Durham. It's a Durham map. This is a Durham map. This is just mod Z. This is I. And this is J. So the rest of the talk will be, what? Oh, what?
K even.
K even, what about it?
I'll put an arrow, the main one above the arrow. K even to H even.
K, oh yeah, I didn't label that, oh yeah. I forgot what I call it here.
Also Ch.
No, this is, oh yeah, I guess this is Ch too. Well, it's kind of tensor with C, isn't it? How do you do this map? Well, yeah, it's a sort of a Ch. So the rest, so I'll put this up here, you can ponder it, and we'll say what things are, but what's in the middle is differential cohomology with respect to K-theory. So before it was ordinary cohomology up in the upper right, ordinary integral cohomology. Now it's K-theory in the upper right. These are various types of differential forms. That's odd C mod K-theory with coefficients in C mod Z. The Box-9 is a familiar name. And so what is all this about? This is a functor in the middle. And I think that this functor is also uniquely characterized by this diagram. There's no other such functor, k hat, which satisfies all this stuff. So, okay. So,
and that's a theorem of Wilkie and Schick. That's a non-trivial theorem.
That's a non-trivial theorem. That's right.
Because K odd is not characterized by the diagram. K hat odd.
K hat odd is not. That is true. There's a diagram with K odd up there and a nice construction in the middle, but it's not uniquely characterized by the diagram. So, anyway. So I want to give the notion of what we call a structured bundle. So these things in the middle are all vector bundles with extra structure. So if I have a complex vector bundle with connection V and a connection which we'll call del over X, we'll let R contained in wedge 2 of X and endomorphisms of V is the curvature. And that's the notation. I'm going to define CH of del, which is the Chern character in terms of differential forms. So it's summing on J, 1 over J factorial, 1 over 2 pi I to the jth power times the trace of R wedge R J times. And that's an element, it's a closed form in wedge even of X with complex coefficients. Okay, so this is the Weil homomorphism applied to these invariant polynomials, the trace powers. You sum them up, you get a form, and this represents the Chern character. This is a rational, it's a rational cohomology class. Complex coefficients.
V is a complex bundle, you said?
Yeah, I didn't say it, but I should have. V is a complex vector bundle. Complex vector bundle.
Delta is a complex linear connection.
And this is a connection, right. This is a connection. This is a complex vector bundle. This is the Chern character. And now, if I have a closed curve, a curve of connections, well, suppose I have two connections. So I have delta 0 and delta 1, and a curve connecting them, gamma of t equals, let's say, delta up a t, I can say that A up a t equals delta t prime. So you take a derivative of this family of connections, and that's an element in wedge 1 of X with coefficients and endomorphisms of V. So when you differentiate a connection, a family of connections, you get one of these. Some of these symbols are going to look like the symbols that Fadeev talked about before, so it's vaguely familiar. Then there's something, so I want to see, there's a difference function. I hope you guys can see this. It depends, it looks like it depends on this curve, so we'll call it CS of gamma, and that equals the integral from 0 to 1 of the sum on j from j equals to 1, starts at 1, of 1 over j minus 1 factorial 1 over 2 pi I to the j times the trace, this time of a upper t, so remember I'm integrating this thing, wedge RT, and this is j minus 1 times. And this is contained in wedge odd of x coefficients in C. So here's a form. R upper T is the curvature of the teeth connection, and it varies. And A upper T we've just defined. And so,
Can I ask a question?
yes?
So if you looked at the formula for cha of the connection,
Cha, yeah.
and then if you imagine that depended on t, if you just differentiated that, would you get that expression?
No.
Because r is dA plus a squared. And
Yeah, but you'd see the T would distribute among all these things, where here it's there everywhere.
yeah, but you differentiate the product, you get like a derivation,
Yeah, but you'd,
and the trace means you can cyclically permute, so you can move the a to the front.
yeah, I don't think so.
Okay,
I don't think so.
all right.
No, because you have to take D of this. If you just differentiated this, you wouldn't get something that,
Oh, I see.
Anything
Anything that changes dimension.
it ain't gonna work. Right, one thing, it changes dimension, right. So here is, so this is a term that connects the two characteristic forms. So if I take the differential of CS of gamma, this is sort of dependent CS of gamma, I'm going to get D of that is going to be the Chern character of delta 1 minus the Chern character of delta 0.
Well, how can I think of that, CS again?
How can you think of it?
Yeah, you just wrote a formula down. I hate formulae. I want ideas. I'm having jet lag.
Well, one way to think of it is if you got the Chern form by a map into the classifying space, and in the classifying space there is this Chern character, and if you had a one parameter, if you had a curve of such maps, and you took the interior product, the interior product of the Chern character over there, interior product with the parameter field of the map, and integrated that, I think you get this. That's a way of thinking of it.
The chain homotopy.
Right.
Okay.
That's right. So such a formula is obviously not surprising because these two things are cohomologous. This gives a particular formula. It seemed to depend on gamma, but actually a good fact is that if gamma bar was another such curve, in fact, gamma bar, another curve then right, CS of gamma hat, gamma bar, this curve, equals CS of gamma plus exact, plus something exact, okay? So therefore, I can just define, now I can leave out the curves, and I can define CS of the pair of connections equals, let's say, CS of gamma modulo exact.
That means theorem.
What?
That means theorem. What means that? This is a theorem?
It's a theorem, but a fact means a small theorem. Okay. It's a relatively unimportant theorem, but useful. Okay. So this is a useful, maybe I could have said
What means exact?
useful lemma, whatever.
What means exact? What is that form?
Exact. It means, so CS of delta 0, delta 1 is now an element in wedge odd modulo wedge odd exact. Exact differential forms, that's what exact means, okay? So this is now a well-defined object in this space. We forget about exact forms, don't worry about them. And it's just a total odd form, modulo exact. So that's well-defined. And here's a nice fact, another fact about it, that if I take CS of delta 0, delta 1, and I add that to CS of delta 1, delta 2, that is actually equal, remember, working mod exact, that's actually equal to CS of delta 0, delta 2. Okay? So you go from this connection to this one, and you can go via this one in the middle, and you'll get the right thing. And that means that this, we're going to get an equivalence relation. So we can say delta 0 is equivalent to delta 1 if CS of delta 0, delta 1 now equals 0, because remember this is mod exact and is an equivalence relation. So because of this, it satisfies this equivalent. Anyway, that's clear.
If and only if.
What?
If and only if.
If and only if what?
The definition, that's true if and only if.
This is the definition.
If and only if.
Right.
People like to write definitions.
All right, I put in an extra F. All right. Anyway, this is a definition of two equivalent being equivalent, and so I'm going to define a structured bundle.
I think it's very worth saying if two things are equivalent, they actually have not only the same characteristic classes, but they have the same characteristic forms.
I'll get to that. I will get to that, but it's true. They have the same characteristics. So I want to define a structured bundle. Structured bundle. And this is equal to a pair, V equals a vector bundle together with an equivalence class of connections. So that's a structured bundle. It's a vector bundle. It doesn't have a particular connection, but it has this family of connections, and that's good enough for many purposes. And because of
Up there.
this formula up here, that the differential of CS is that, and those two things would differ exact. So ch of V contained in wedge even of X coefficients in C is well defined. So if two connections are equivalent, they have the same Chern character, and
As differential forms.
as differential forms, yeah, same Chern character. So chush is now a thing, and there you see that chush up there. It's the same chush. It's the same chush. Okay.
One question. So a priori you could have required just the equality of Chern forms, but you impose a stronger condition, right? So
Yes.
equivalence is a stronger condition.
Its equivalence is a stronger condition than the Chern forms are equal, yes. And that's really an important point.
And it's going to be a better condition, right? Because so your diagram will work because it's a better condition.
Exactly,
So-
exactly. But if I just said they're equivalent, if the Chern forms are equivalent, it would not have been a very interesting, it would not have been very interesting. But this is interesting. It's obviously more subtle. Now let's see. Next thing to do is array. Yep.
Comment on that last comment you made?
Yeah.
I mean, saying that Chern forms are equal is specifying infinitely many parameters, right? Obviously, it's a form. And this extra precision is, in usual cases, is adding only finitely many additional parameters. However, it makes the mathematics work correctly. Like there's going to be a Marvius-Torres property that doesn't hold if you put this equivalence relation, but it does hold with this thing, things like that. There's
Yeah.
only finitely many more parameters. So, but it's the correct thing to do.
When Dennis and I, so this is work that Dennis and I did, and we were searching for a candidate for this guy in the middle. And we said, oh yeah, well, the Chern forms should be the same if we're going to use bundles, but that just wasn't, it just didn't work. It wasn't enough. And then, oh yeah, well, something, we have to say something about the connections, and this is like the minimal thing you can say about the connections that makes this thing work. So, let's see. We go a little bit further here. So we have these structured bundles now, and you can take a direct sum of two connections on the direct sum of bundles. You can take the tensor product of two connections on the tensor product of bundles. And that all makes sense. It carries through with this equivalence so that we can really talk about V direct sum W or V tensor W if V and W are two structured bundles, obviously you take the direct sum of the bundles, you take the direct sum connection, and over here you take the tensor product of the bundles and the tensor product of the connections, and the equivalence holds. So that this two things are, well, you see what you need. This all makes sense. And so now, and as Dennis pointed out, shush, oh, did I write it already? Yes, I've already written it, it's well defined. So now, I'm going to define something called struct X. So struct X equals the abelian semigroup with distributive multiplication. What?
It's like a semi-ring, I guess, too.
I don't know what you call it. An abelian semi-ring.
A semi-ring, can you say that?
You could say it, but I don't know if it's an official definition.
Oh, with the distributive multiplication. Oh.
Anyway, it's abelian as a semigroup, and it has a distributive multiplication. And yeah, with commutative distributive multiplication. Anyway, it's an abelian semigroup with that stuff. And I want to look at isomorphism classes. So it's the abelian of isomorphism classes. Of structured bundles.
So, if you read the Tina's book on K-theory, it talks about vect X. The same thing. This is, we're copying his, Jim's copying his notation.
Right.
X, right?
Yep.
Remember that? Yeah.
Sure. Yeah, you got vect X. So K, you remember, you make vect X, which is the isomorphism classes of vector bundles.
Honest bundles, right?
Honest bundles, forgetting about connection, that's vect. And then you apply the growth of deconstruction, and you get K of X. You apply that to vect. And here, obviously, we're going to apply the growth of deconstruction to struct. But it's a little more, it's a little more work. So here's something that's analogous to ordinary vector bundles. Well, if I take all right, so I'll make it all right. Definition. A connection is called flat if holonomy holonomy is trivial. It's actually V. This pair is called flat if it has trivial holonomy, and that means the bundle is trivial as a bundle, and the curvature 0, so it implies V trivial, curvature vanishes, and so we'll call.
Can I make a comment? People usually write little f lat, and that means
The curvature
curvature is
vanishes.
zero, which means it's a flat bundle. So he means the global holonomy as well as zero, so it's capital F. So
Right.
not only is the bundle trivial, but it's the trivial connection. Is that,
It's as trivial as you can get.
yeah, flat capital F.
It's a capital flat. I mean, it's flat as can be. Boring as can be. And so we'll call V contained in let's say V represented by V and a family here. We'll call that flat. If some del connection contained in here is flat. Is flat. So we'll have flat objects in here. And now here's a nice fact which I'm going to dignify with the name of a theorem. Yeah?
So in this last definition, the bundle itself
It's trivial.
is trivial.
Correct.
I mean-
Bundle's trivial.
No. In the very bottom line, the bundle, is it trivial?
Yeah, the bundle is,
Same
yeah,
bundle.
yeah, it's this bundle. Right,
I got it.
yeah, I should have put,
Here is in the word is. When you say a bundle is trivial, that's not a very good sentence. A bundle is an F that can be given with an isomorphism as a trivial bundle. That's different from saying a bundle. You say a bundle is trivial, it means it is the trivial bundle.
yeah,
A bundle is isomorphic to trivial bundle. It's an abstract bundle, isomorphic. So flat bundles are these abstract bundles with given isomorphism to the trivial bundle.
right.
Okay. Okay.
Because he's building a set out of this
Right,
collection of objects, so.
right. Now, any two such flat guys of dimension n are isomorphic. So,
A guy is an element struct.
right. Guy's an element struct, but they're all isomorphic if you have a dimension n. So so n is the only thing important. So we'll call this, what do I call it here? N contained in struct is this, I mean, it's an element of struct. Is that guy. That element. Okay, so now, so here's a theorem. Given V contained in struct, can find W contained in struct such that V plus or direct sum W equals N for some N. So this is exactly The same statement for ordinary vector bundles. There's always an inverse. You can always find some inverse. It's not unique, but there it is. Now, the proof of this.
The question is
Yes.
about the notation.
Yeah.
N, this n in brackets. I suppose it is n-dimensional vector bundle, n-dimensional vector bundle trivial with trivial connection.
It's trivial. It's one of this isomorphism class of trivial n-dimensional bundles.
The first 3 lines give a correct statement of what that means.
Yeah. So now this theorem is not trivial to prove, and in fact, the proof that we gave in our paper really only worked the way we gave it for Hermitian vector bundles where the structure group was a unitary group rather than the full linear group. Because, well, anyway, but it's nonetheless true, and Leon, sitting right over here, found our error, regrettably after the paper was published, and found a shortcut, fixed it. So, but this is true, and it's very useful in here.
Well, I think the better, maybe slightly better from it, Leon was doing a kind of a holomorphic analog of this theory, found a different proof, and then he noticed that this also helped correct the inadequacy in our...
Well, he pointed out the inadequacy.
He found the inadequacy and then solved it at the same time.
It was kind of a subtle point. Narasimhan and who's the other guy? Ramanan and Narasimhan proved years ago that all bundles with connection with any group and so on could be gotten from a classifying bundle. And with vector bundles, the traditional classifying bundles are those over the Grassmannian, and that classifies all vector bundles. Well, that's the classifying space, is the Grassmannian, different Grassmannians. And that turns out to be, and they all have canonical connections actually, and it turns out to be that classifies bundles with connection where they are unitary, when they have a unitary connection. It does not seem to classify bundles with connection when, well, they don't know. There is a classifying bundle, but it's not necessarily that one. It's not necessarily that one. And I had misread the theorem, thinking it was always that one, and using that bundle, which comes equipped with an inverse, comes equipped with an inverse. The bundle is everything in the plane or in the subspace point of the thing, and the other bundle is the vectors in the orthogonal subspace. So it always came equipped with a nice inverse. So anyway, but this theorem is true in general, and it now is completely analogous to the comparable theorem in K-theory. Okay. So
Speak about structure groups of these structured bundles.
Say it again.
Could we speak now about structure groups? Like for ordinary bundles, the structure group is unitary.
Well, not ordinary. If we were talking unitary here, then I wouldn't have needed Leon. But this is the general linear group. We're just doing the general linear group. If one was doing the unitary group, all the C's would turn into R's, okay? And the theorem is perfectly true if you restrict yourself to Hermitian vector bundles, the unitary group, and so on. Then there's just R's up there instead of C's, and well, it's also very nice. It's really very good. But if you want to go to C, then it's a little bit more subtle.
It's kind of useful, I think, in algebra and maybe number theory to use C. There's some connection with those areas.
Might as well.
Unitary theory doesn't quite.
Yeah, you might as well. All right, so I haven't said anything yet. Oh, but I need this. So now we're going to just set k hat, which I said. So we'll just set k hat of x equals the commutative ring. So you don't have to say semi-ring anymore. Commutative ring obtained from struct of x using the Grothendieck construction. And
Since the point of the talk, can you bear down on the k hat of x? It's invisible to me.
this k hat is invisible?
Yeah, to me, yeah.
Especially hat.
Well, is that more visible?
Yeah.
It's the product. The problem is the water.
Right.
Yeah.
No, but I mean,
there is a dry.
just do it again. Okay, it's kind of emerging now. I can see it. X.
Is there anyone beside Dennis who could not read that k hat?
I can't see it.
No, you don't count. Okay, so that's what that is.
And then that's the k hat up there.
That's the k hat up there. Now I want to define wedge BG. See, wedge BGL. So wedge BGL is of x equals all forms, all closed forms even forms representing Chern characters of vector bundles over x. Okay? So these are all closed forms, and these are a ring because the Chern classes multiply if you have two vector bundles. So it doesn't necessarily say they all come from connections, although it turns out they do. But that's what this is. And of course, this map here takes you into there because it's come from some vector bundle inside there. The map del, of course, is just forget the connection. So that's an easy map. You got this pair, isomorphism class. Forget the connection and you get there. Calculate the Chern character you get in here. And the fact that this thing commutes is obvious.
There's a question.
Yeah, so this lambda BGL, you say it's a ring, but it's not a vector space, right?
No, it is a vector
Or
space.
it is a vector space?
Yeah, because the direct sum.
But if you, or which coefficients?
Say it again?
Over complex?
Complex coefficients, yeah.
Over complex, is it?
Yeah, vector space.
Point is that the Chern character, the refined Chern character is additive.
Yeah, the Chern character is additive and it's multiplicative, so that's okay.
Well, that's a good question, because usually characteristic classes aren't additive. That's the whole point of the Chern character, makes it additive.
Right. Right. The total Chern class of a direct sum, you have to multiply. But the Chern character, see, the total Chern class is an integral class. Chern character has these coefficients and it's additive. It's the log, I guess, or something.
It's mysterious, right? We don't know exactly what it is, right? You define it as all forms coming from Chern characters, but it's intrinsic.
What, this space here?
From the BGL, yeah.
Yeah, that's right.
It's
That's
a
right.
mysterious object. Right?
It is, but another way to look at it is all forms that you get from,
Stabilizing.
well, from mapping into the big classifying space. From mapping into the classifying space and pulling back those canonical forms. It's a little mysterious, but there it is, and it's a perfectly good thing.
Well, it's not mysterious, it's all, I mean, you just said it, they all come from connections on stabilized bundles.
Yeah,
So they're all Chern character forms of all connections on all bundles.
right.
Right, but are they all forms integral? Or
What?
are they all forms closed, even? It's a Hodge conjecture, right in here. Complete description of
I don't
this.
understand the,
Complete description of this space would be a Hodge conjecture.
No.
For complex manifold. The image, if you know the image of all Chern character magic.
Maybe for a complex manifold, but
Complex manifolds is a Hodge conjecture. Complete description of this.
oh, I know what he's saying. I know what he's saying. It's not mysterious, because, oh, that's gonna come up in my talk. I'm gonna give another formulation of this, and I'm gonna say lambda BGL in terms of a topological condition that characterizes it. It's the integrality condition given by the Etias integration. So, I see his point. See, which cohomology classes are Chern
Right.
characters of bundles? So
That's the question.
the
Yeah, that's
topologists
exactly.
have solved that. That's known from the 60s. And I'll mention it. Okay, fine.
So this is
right.
Got what you meant.
I just define it as it's coming from bundles,
Right.
and Dennis will characterize these things coming from bundles by some integrality. All right. So there's one more thing, and then I'm pretty well done. Pretty well done. I want to go back to,
Wait, so you're saying K hat is defined here, fits in there, and
Yeah.
everything is defined now?
yeah, but no, this isn't. Wedge GL is not defined.
Okay.
So I want to define wedge GL, and wedge GL will be kind of familiar. So we go back to the group GLN. We go back to the group GLN, and so we have GLNC, And on GLNC, there's a canonical Lie algebra valued 1 form. Oh, thank you. So, theta contained in wedge 1 of GL and C with coefficients in its Lie algebra that I'm just going to write that. Gosh, anyway, you know the Lie algebra, this is this. There's a canonical form. It just says take a tangent vector at the identity that is an element of the Lie algebra. You push it around, it's a 1 form with values in the Lie algebra, left invariant 1 form with values in the Lie algebra. That's little theta. And then we define some great big thing, capital theta. And I'll give you a motivation for it in a second. So it's sum from j equals 1 bj, whatever that is, of the trace of theta wedge theta 2j minus 1 times. They're all odd forms. Okay. That's contained in wedge odd of GL and C, where Bj is a crazy number. It's 1 over j minus 1 factorial times 1 over 2 pi to the jth power times some number which is best written as the integral from 0 to 1 of t squared minus t to the j minus 1 power dt. I tried to simplify this somehow, but anyway, that's the coefficients. And really, this total form, which represents a cohomology class in the group, is the transgression of the Chern class. And so...
Not the Chern character?
Chern character, yes. Thank you, of a Chern character. So if you use the Chern-Weil homomorphism, you may remember from yesterday, you have this invariant polynomial, these trace powers, those invariant polynomials in that Lie algebra, that generates all the invariant polynomials. And if you take this particular one, upstairs it's exact, it's d of something, you take that something of which it's d upstairs, you restrict to the fiber, and you get this. And that's the transgression activity. And this is a nice thing. Now, and so wedge GL, so now wedge GL of x equals G star of this guy, big theta, plus wedge odd exact where G here, G maps X into G, L, and C, all such G's. So, you map X into the group, you pull back this form under that value, you do that for all possible maps of the manifold into the group. And then, for good measure, you throw in everything exact. In fact, I've often wondered if you can get all those exact things from maps into the group, but it doesn't matter. There it is. So this is wedge GLN. And so what's the motivation for defining this? Well, it's the following, and it's kind of a nice fact. So I'll just say it. So suppose you have a flat bundle and it has two isomorphic connections. Well, that you get from like a gauge transformation. You just transform everything, you get another connection. They're both flat. But they're not equivalent. When you take CS of a pair of isomorphic connections, the CS term does not, in general, zero. That is to say, that form is not exact. But it's exact plus one of these guys. So isomorphic connections are not necessarily equivalent, even if they're in the trivial bundle. In any event, they're not equivalent, but they're almost equivalent. Instead of CS being exact and therefore zero, it gets perturbed by this map. So notice if you have at least a flat bundle and you have two connections, one relates to the other, they're isomorphic. So there's a map from the base into the group. You can do that. So that's why we define this guy here. You need that. Now,
Can I add to this, because
yes.
I'm sure this was a little confusing, and in fact it's going to be very important in the next half, because in fact we argued about this for years. In modern mathematics now, we're moving from set theory to category theory essentially, and one has to distinguish between the word equivalent and equivalence.
Oh.
There's a difference between two things being equivalent and choosing an equivalence between two things. So he's just made that distinction. Two flat bundles are equivalent, but the equivalence may change things.
Yeah.
So there's the idea of a structure on a given bundle. You can deform it to an exact Chern-Simons equivalence, and that's an element struct, but you can have an isomorphism with an automorphism that changes the equivalence class.
Yeah, it changes the equivalence class. But it doesn't change it by much. So you have to allow this extra thing. So I'm almost finished. And I'll finish over here. And then we'll go back and look at the diagram again.
Information is bad too, so I didn't say it again. My fault.
So we'll call V contained in struct or stably trivial. That means that there's a V direct sum something flat equals something else flat. That's what it means. You can add a flat element of struct and the sum will be that. That's stably flat, or stably, maybe flat is what I meant, stably flat. And here's the thing. if V is stably flat, you can construct, which I'm going to call capital, I'm going to call it CS hat of V as an element of wedge odd modulo wedge GL. Modulo wedge GL. So now I didn't have to take two guys if this thing was stably flat to get a CS term. I can get sort of a CS term if I'll allow some ambiguity by just one connection. Because if I took a second connection on this stably flat, see, remember GL contains all exact things too. So because it's stably flat, suppose it was actually flat. And I take a connection, I take another one, they're related by a G, map into the group, and I'm going to get something in here when I take the CS term. So if I want to forget about these things, I can actually do this for all stably flat. So this is, and here is another fact, which is pretty important. In fact, it's very important. That this map, CS hat.
You know, there's something wrong. This B plus F, I think that's some connection on the trivial bundle, but not the trivial bundle. Trivial connection on the trivial bundle. So you're saying that stably, because you're trying to characterize what goes to zero in K theory, right?
Yeah.
So that just means there's some connection on the trivial bundle, which when you add it into your given structure bundle, gives you the flat guy.
That's right. That's right.
But you wrote V plus flat equals flat.
Yeah.
Isn't that V plus some connection on the trivial bundle is flat?
See, notice that this is the kernel. I mean, these things, if it was just bundles, this is the kernel in K theory. This goes to zero in K theory, ordinary K theory, right? Anything stably trivial, it's trivial. I mean, it goes to zero. I want to see what the whole set of things that go to.
How are you doing that?
Yeah.
See, any connection on the trivial bundle goes to zero.
Yeah. Let me see. Did I write this down wrong? I want to look at the kernel of this.
Yeah.
And then I guess I mean, yes. Okay. I wrote this wrong. It's stably trivial. If V is contained in struct, let's just put trivial over here. So if you have a stably trivial bundle, then you can define this if it's stably trivial. You can define this by itself.
By the CS.
Yeah, suppose it was trivial. Suppose it was trivial. Okay, this is how it works. Let's just suppose it's trivial. It's a trivial bundle. It's not flat or anything.
Some connection on it.
Right, with some connection. So I pick a trivialization, and the connection. I fixed that. And now, any other connection will give me a CS difference. But now I say, oh, well, suppose I picked a different trivialization and a trivial connection with respect to that. Then the CS term would be different, but it would only differ by the difference of those two flat things. Right. And therefore, if it's stably trivial, I can construct this. So forget the stably flat line. Forget the stably
You have a bundle which is trivial and a connection on it. Trivialize the bundle, take the CS term. If you change the trivialization, you change by lambda GL.
Right.
The CS term will change by lambda GL.
Yes.
Okay. So that's it.
So, and in fact, I just sort of waved my hands and showed how you do it if the bundle is trivial, but that it works even if it's stably trivial as a bundle.
Bundle just over a point.
What?
Suppose I take a bundle over a point with a non-trivial connection.
A bundle over a point.
All the connection will be trivial.
All the connections will be
All the
trivial.
connection.
Now that's maps of a point into GLM.
Yeah.
Okay.
And then you're pulling back this odd form.
There's no, you can't differentiate nothing. Everything's collapsed.
Maps of a point. If you have a vector bundle over a point, the different isomorphisms of the trivial bundle is GLM.
But if I
So
take
you have a map of a point and a GLM.
Right.
So it's consistent.
All right. So here's a fact. CS maps. The fact is that CS I wrote it. That CS on the kernel of delta into wedge odd GL is an isomorphism. And so I make I, so I'm going to set the I above equal to CS hat inverse. Okay? Now this took some work, takes some work to prove. And again, it depends on that inverse construction. So the fact that this is true in the non-Hermitian case,
Again, we thank Leon.
again, we thank Leon. So Leon, I mean, the paper is published. No one knows that it's wrong. But nonetheless, it has that error.
Still might be okay.
Well, the theorems are correct. It's just that the proof is wrong. So the fact that this CS thing, you can get an element in here seems reasonable. If it's something that's trivial or even stably trivial, okay, I can get this total form modulo these GL ones, well defined. But it's kind of nice that everything in there gets, the whole thing slides right in to K hat. That no matter what odd form you take up to something in GL, there is in fact some bundle with that as its CS term, some trivial bundle or stably trivial bundle with that as its CS term. And that, since this is full, and because this is closed anyway, it doesn't matter under D, it shows that every form over here arises as a characteristic form. Every form that's homologically appropriate is the characteristic form of some bundle with connection. That was not obvious.
What
So,
does it mean homologically appropriative?
Say it again?
What does it mean in this context, homologically appropriative?
that its cohomology is that of the Chern character of some vector bundle. Yeah. So it's cohomologically appropriate, cohomologically appropriate. That's what wedge.
Characterize that next time.
That's what wedge BGL is. Those are all those forms, appropriate forms. Everyone comes. So, but the map chush is onto. They all get hit. And the fact that chush is onto comes from the fact that this covers everything. Obviously, chush is onto, cohomologically it's onto this, but that every form shows up means that you could add D of anything, and you'd add something exact, and that's because this all fits in there and therefore goes over there. So I'm going to stop here. There's a lot of details, obviously, but this is a representation, a model for K hat. It's a model for differential K theory. There are other models. Turns out they're by Bunke and Stieck, a German pair. They are all isomorphic, so there's only one actual functor up to isomorphism. But there's a number of ways to see this. And notice, this is very different from differential characters. Differential characters were functions on cycles and so on and so forth. This is equivalence classes of connections. Really different. Now Dennis is going to talk about how actually you could make a model for K hat in terms of functions on cycles. And so I guess we'll stop and then we'll come back and we'll
Thank you very much.
listen to that. Okay.
So I think Jim's talk yesterday started with, he was trying to compute the first Pontryagin class divided by 3 in a combinatorial manner, because that gives the signature. And that means the integral of the first Pontryagin form divided by 3 over the manifold, 4-manifold, is an integer, because it computes the signature of the homology, the middle intersection homology, so it's an integer. So this quantity is an integer, and in fact, this would have been known to Pontryagin, or Pontryagin defined these classes, and probably Rocklin proved that it was given by the signature. Then turns out that's if you have a smooth manifold, but there are 3 other kinds of manifolds that can come into play besides smooth manifolds. You can have spin manifolds, almost complex manifolds, or stably almost complex manifolds. So when I refer to a C manifold, I mean a stably almost complex manifold, which means a stable tangent bundle has a complex structure. Or spin C, I'll say what that means effectively, I won't give the definition. But anyway, so it turns out if the manifold is spin, then actually 4-manifold is spin, P1 over 24 is an integer. And in fact, there's a generalization to higher dimensional manifolds using something called the A hat genus, and this is always an integer. And the topologists found this out. Adams, Bott, Milner Bott proved the Bott periodicity theorem, and then Adams and Milner extracted the maximum information out of that and got that certain things are integers, in all dimensions. But already in the late 50s, I think Rocklin found that actually P1 over 48 is an integer for 4-manifolds, and this turns out to be the significant fact that distinguish, 4-manifolds. And I'm talking about P1. So to be an integer, you have to integrate. Yeah. And so in fact, this is the fact that this is an integer generalizes universally, and then there's an extra factor of 2 Rocklin discovered, which later gave these interesting conditions that whether to be a smooth form manifold is an extra subtle condition. And then Donaldson gave more conditions. His famous theory gave more, but Rocklet already had the first non-trivial condition. Anyway, so there's integrality issues that are quite subtle here. And so for these three kinds of manifolds, so if you take an even closed manifold and a vector bundle over it, complex vector bundle say, or a spin bundle, or I haven't said what this is, I will in a minute. Then you can form the Chern character cohomology class or form, and then you can combine it with an internal characteristic class of the manifold. So it could be the generalization of some of these things here. Anyway, and it was found by Adams, Bott, and Milner less than 1960 that these combinations gave integers. Then I think Gelfand independently raised the question of, the index of an elliptic operator is an integer, and if you deform the operator, this integer doesn't change. It varies continuously, so it doesn't change. So it's a topological invariant, and how to compute it. So that's the famous Atiyah-Singer index theorem, where it's formulated and proved. And in fact, the story of that theorem is sort of forgotten now, but actually the fact that these expressions were integers, which were proven by the topologists, meant if that's an integer, it should be the index of an operator. And so Atiyah and Singer invented the Dirac, they named it the Dirac operator, but they invented the Dirac operator in the full differential geometric context. And you need a spin structure to work over R. If you work over C, this other structure called spin C is enough to define a Dirac operator. And then the solution space, its formal dimension is the integer in question given by this formula. And then the question that Leon asked last time about what is this image here? Well, Jim said, well, this really only depends on the cohomology class being appropriate. It's closed form. So I'm going to, abusing history, I'm going to call this the Atiyah-Singer space. Okay, but it really should be the Bott, Milner, Adams space. But it's easier to remember if you think of it as it's more elegant. I'm going to call this the Atiyah-Singer space. And so the statement is, here's a proposition. Suppose you have I'm going to say it in the stronger form. I could say it, a cohomology class is a Chern character of a bundle if and only if. But I'm going to combine it with what Jim said. So an even form on a manifold is the Chern character form of some complex bundle if and only if for all even closed manifolds mapping into the base, when you pull back this form, this expression, see if you put in Chern character of E, this would be an integer. So this a necessary condition that this is an integer. So that's a sufficient condition. That's the theorem. So it's extremely beautiful. So in other words, the theorem is the form is a Chern character form if and only if it satisfies the well-known integrality conditions that are expressed by the Atiyah-Singer index theorem. And the integer in this case is the Dirac operator of the manifold with coefficients in the vector bundle. You can make coefficients in a vector bundle. So that's the integer. So if you want to know whether a certain cohomology class is appropriate, you just see if it satisfies these integrality conditions. Then there is a bundle, and these integers become the indices of Dirac operators with coefficients in the bundle. So that's the answer. So it couldn't be any nicer, huh?
Just for arbitrary form from the beginning.
What?
Arbitrary form from the beginning and then.
What? Arbitrary form from the beginning. Then you have to test it on every closed manifold mapping in, and you have to get an integer. It's a necessary condition, and it's sufficient. So that's the statement. You can never forget it. I mean,
what is C in the
huh?
What is C? It was not
C is the arbitrary form that you want to see is at a Chern character. So you have a arbitrary base. You want, is there a bundle up here so that this form becomes the Chern character form. So you take every manifold mapping in, closed manifold, you pull back, you see whether it satisfies the integrality condition, which it would. See, if the bundle was there, you could pull back the bundle, form the Dirac operator with coefficients, and then that formula gives an integer. So it's necessary. So the statement is sufficient. Okay, now, I don't know who to attribute this theorem to. I'll put down a few names: Stong, Hattori, and maybe myself, because I knew the theorem, and when I looked it up, I couldn't find it anywhere. So anyway, it follows from some other information that one had in the 60s about topology. Anyway, and it's we have a paper in Jeff Cheeger's memorial volume where we state this theorem. Okay, all right. So that's the and now there's another wonderful theorem besides the Atiyah-Singer index theorem. There's the Atiyah-Patoti-Singer theorem. This is the early 70s. See, this theorem here is like early 60s. See, and this is less than 1960. The integrality was known, and they were finding, hey, if it's an integer, it must be the index of an operator. Well, that's how they. And this is Atiyah-Patoti-Singer. Atiyah, Singer, and then Patoti. And this is when you have a manifold with boundary. And I remember watching Atiyah talk about this theorem. He would write down a formula, and he would say, this term is analysis, this term is differential geometry, this term is topology, and they add up to 0. So, you know, Atiyah likes to sweep, you know. So the topology term, well, if you were doing the appropriate ordinary manifold without the additional structure, would be the signature. That would be an integer. Otherwise, if you're doing one of these others, it's like the holomorphic Euler characteristic, or the arithmetic genus, or it's called the A-hat genus, but it means the dimension of harmonic spinors, either real or complex. Anyway, there's some integer here, and when you have boundary, you have to put boundary conditions. The boundary conditions are kind of subtle, but anyway, this integer measures some natural thing like that. And then the differential geometric thing, this is some integer, and I'm going to be reducing mod 1, so I don't emphasize this integer anymore, although the fact that there is an integer there is crucial. The differential geometric thing is, this is the term you integrate over m, you integrate this expression, which might be an integer. You integrate this over, let's call this w now. Let's use w when you have boundary. So you integrate this thing, that gives a real number. When it's a closed manifold, it gives an integer, but it gives a partial integer, or a real number. So that's what you put here. And here you put the integer, which has some sort of topological condition. It's the index of some operator with boundary conditions. And then the analysis is, we have an odd dimensional manifold here. When you look at the same operator sort of on the boundary, but now it's self-adjoint, so its signature is 0, and you look at something called the spectral flow, you look at the spectrum, it's self-adjoint, you make a zeta function, do analytic continuation. Anyway, you get a complicated number, and this is called the eta invariant. Eta invariant. Anyway, so this real number and this real number differ by an integer, which is given by topology. This is differential geometric, integrated over here. This is a spectral invariant of the boundary. This could be, if you don't know how this fills in, and you just give the differential geometry on the boundary, you can compute this number from spectral theory, but it's not really computable. Whereas this number is computable, and this number is an integer. So this number is computable mod 1 because it's just this integral reduced mod 1. Okay. So now, what we want to do, so this is what we have as our machinery. We have this integrality and these wonderful theorems here. And then there's another theorem, another thing we have is another, from topology, there's the notion of a homology theory. So first let me remind you of this sort of fantastic theorem around 1950 of Steenrod and Eilenberg-Steenrod, giving axioms for homology. So if you have a functor which is into space into graded abelian groups, which if it maps by homotopy, the induced transformations are the same. You have the excision, you have it defined for pairs. There's the excision isomorphism. You have the long exact sequence of a pair. They have three axioms. So let's call them homotopy, excision, and exactness. And then you have the statement that the homology groups of a point are concentrated in degree 0. Then those four axioms uniquely characterize the functor. So our theorem that Jim talked about yesterday is was sort of just trying to do an analog of that for ordinary differential cohomology. Then a generalized homology theory is where you only have the first three axioms, you don't have the axioms of a point. Okay, and now so that's the definition of a homology theory in general. And Whitehead gave a representation theorem, which is very useful, so you can represent this in terms of homotopy theory, stable homotopy theory. But now it's not unique. In other words, the groups of a point don't determine. So K theory, and then Bott's periodicity theorem gives an example of this. So that gave the first serious example of a generalized homology theory. Tom's work, Bordism theory, gave other examples. So there are lots of interesting examples of generalized homology theories. They satisfy the same axioms except the groups of a point are different. And then the uniqueness theorem requires you to understand the theory of what's called spectrum in stable homotopy theory. All right, but being a homology theory is quite significant. In other words, there's things you can do. So for example, you can talk about homology with coefficients in anything. So the homology with coefficients can be defined because of this definition in terms of homotopy theory. So you can do that. So you can take coefficients and you have the Bachstein sequences and stuff like that. So you have this thing across the top for K theory. That just follows from being a homology theory and Whitehead's representation theory. And then you can build homology theories out of other ones. So for example, if you look at this theorem here, there's a natural product structure. If you take one of these problems and cross it with another closed manifold, so you take V mapping to a point, M mapping into X, and you take the product mapping into a point cross X, which is still X. So there's a natural module structure. You can multiply these elements by closed manifolds mapping to a point. Then, because of the multiplicative property of this guy and the fact that there's nothing mapping to a point, this number will just multiply by the Todd genus of V. If you compute this number and then do this and compute this number, it just differs by multiplication by the Todd genus of V. So I'm going to call that the product formula. An obvious product formula. Now you can say, well, so this is the notation we use for these things. If we consider these maps here, closed manifolds mapping into X, and then we took, this would be M1 and M2, and all this is mapping into X, and this is again a manifold. And if the almost complex structure that you have here and here extends over the middle, then we say these two cycles are homologous in the Bordism theory. Okay? This is like homology theory. And when we take homology classes, we get a homology theory. I put the star down here. This is Bordism, complex Bordism of X. Okay. So this is a homology theory, and this is a cohomology theory. And then there's another surprise coming from topology, which is due to Connor and Floyd. I use this a lot in my thesis work and stuff. And it's nice in those days to be in Princeton, because then they came by and gave lectures, because in those days you didn't, papers didn't appear on the internet. You know, there were preprints maybe, and then it took a year before they were published, and so it's lucky to, so I got in on this before this was even published. Anyway, they proved something that was quite remarkable. In fact, I still hardly believe it. You can mod out by this action here. You can mod out, if you multiply, see this is an action on the bordism. You can cross with V, mapping to a point. And this is a module structure over this ring. And then you can collapse under this Todd genus homomorphism. So you can cross with V here and then identify that to the Todd genus times Todd genus of V times that. So let's see, this is over the bordism of a point. And this module structure is the Todd genus. This is a ring homomorphism. So the Todd genus is this, it's like holomorphic Euler characteristic. It's multiplicative map. So what I'm doing is, what you're doing is you're saying MF, you're saying this, suppose you cross with something whose Todd genus is 0, you're setting this equal to 0. If Todd V equals 0. You're adding these relations. So if you cross with CP1, the Todd genus of the sphere is 1, and that doesn't change the element. So this is, sometimes this is called the periodicity relations. And now, if you consider this thing, this is the homology theory. It satisfies these three axioms, homotopy, excision, and exactness. Well, if you do any algebraic construction to a homotopy functor, you're going to get a homotopy functor. If you do any algebraic construction to something where there's an isomorphism, excision, you're going to get an isomorphism. But if you tensor an exact sequence with a module like this, you're not going to get an exact sequence. There's this idea of a flat module, which essentially means it's essentially free after you localize it. These modules are super non-free and super complicated. And Connor Floyd proved this functor still satisfies the exactness. This is the homology theory. So this is a surprise. So this is something, if you knew enough, you would say this is impossible to happen, but it happens. So everything that subsequently now, everything that follows now is basically just going to be standard work using this beautiful integrality stuff and this stuff, this fact here, everything else. And in fact, what they do, they actually go on to prove that this theory, if you look at the groups of a point, it's just Z, 0, Z, 0, Z, 0, Z. It runs down to minus infinity because you've collapsed all the bordism down to this one Z. And in fact, this homology theory is the dual homology theory to K theory. That's also what they prove. So now we have, let me just back up a second. I remember before I started working with Jim, a few years before we started working together, we were in Manhattan at some dinner for IHES, and Maxime Kontsevich was there, and then we were walking afterwards home, and then Jim joined us. We were walking along. We walked him home, and we were talking about math and stuff, and Jim was asking us, what can you say about a vector bundle if all the characteristic forms vanish? Not just the characteristic classes, but the characteristic forms. So, interesting question. Or, you know, what can you say when two vector bundles with, I mean, what can you say about what can you say about a connection if the characteristic forms vanish? And so, you could also say, well, what can you say about two bundles with connections if their characteristic forms are equal?
you know, how are they related? And then I remember Kontsevich pointed out, well, of course, we know if you say the curvature is that what you call the yeah, this is what you usually call the curvature. I'm also calling it this. This what? R maybe R. R, yeah, okay, R. Well, we know when the curvature is 0, that means it's a flat bundle and given by representation. And then I think Kontsevich pointed out that this makes sense too. This has invariant meaning. So you can talk about that. So anyway, there are various kinds of things. See, we know what this means, we don't know what this means, and we also didn't know what it meant for the characteristic forms to be 0. So these, you know, can look at it and so on. And so this theory actually gives it does two things actually. It gives sort of an answer to that question. Namely, you take these structured bundles and you refine them by finitely many degrees of freedom. That was this question we had, the person who was there talking. It's not quite the same as having the characteristic forms equal, but it's a finite dimensional refinement. And then you make a theory out of that. And so that's, in a way, looking at this question. What does it mean when two things are equal? And then so it fits into a diagram like this, which is now becomes part of a generalized notion of cohomology theory called differential cohomology theory. So it also gives, so this simultaneously gives a representation for something that is interesting, differential K-theory, and at this, that's what Jim's talk was, and it also answers, in a sense, this question. Characteristic forms are equal, or a little finite dimensional refinement means that it's a functor which differs from K-theory by this, or differs from this other kind of K-theory by this, and so on. Okay, so now this business here, with all this integrality and this sort of miracle of Connor-Floyd, that you have a homology theory here, because exactness should not hold here, but it does. Will allow us to give a second geometric representation of this. That's what we're going to, and let me just quickly outline what, and then there's a problem that I've been hearing about for a few years, about 8 years ago. Singer was working on it, and Fried and Lott, Dan Fried and, what's Lott's first name? Lott? Huh? John Lott, right. And Bunke and Schick, Thomas Schick in Germany were working on this. And there's another development in the index theory which is called the families index theorem, which is quite interesting when you do it for families. And then you wanted to have a families index theorem for differential K-theory. So let me just, so then, now yesterday Jim was talking about what he called differential characters. These were functions on cycles to the circle. But now we're going to talk about not just singular cycles, but smooth manifold cycles. So these are going to be odd dimensional, smooth manifold cycles, and they're structured by either this or this. I'm not going to discuss this today. This involves getting into other kinds of K-theory. So take this out now. And so a K character by definition, a K character on X, say X is some big manifold. So here's X. And just like here, if we want to see whether something can be the characteristic form of a bundle over X, we have to probe it by mapping manifolds into X. So here we're going to probe, but here we map in even manifolds. But here we're going to map in odd manifolds mapping into X, and they should be structured. So they have to be provided with, on their stable tangent bundles, an almost complex structure or a spin C structure, which I haven't defined yet, and they should also be provided with a connection. Then, so you have such a thing, and then to any such thing, you have to give a number in R mod Z. And it has to satisfy two properties, that whenever the odd thing is the boundary of something. This number, there's some differential form C on X. So this, the function phi, or maybe call it f, like yesterday, there's a C sub f on X, so that this number, let's call this, let's see, odd m w. So this first property says that f of m in R mod z is equal to the integral over w of this partial quantity c, f star of e, c, times Todd w integrated over w mod z. So you could sort of say, you could express this sort of differently. You could say if you had an m1 and an m2, you got two numbers. The difference between these two numbers is given by integrating the characteristic form over the interior. That's one property. And then the other property is if you cross this cycle with an even dimensional guy in a point, then the number should just be given by multiplying the number in R mod z by the Todd genus of V. Okay, that's what a K character is. So it satisfies a variation property. When it varies by this differential geometric term. Now, because of this theorem, well, okay, you cannot, if you're perfectly intelligent or something and absorbing all this perfectly, you would say, oh, this theorem means you can rewrite what I said in terms of the 8 invariant, but forget that now.
Question about notation. Your integral is over W,
yeah,
right?
That's a good point.
Yeah, but there is no W on the Labot right?
Yeah, there is.
Okay, good. Thank you.
And also here. I had it here.
Okay, now I got it.
Yeah. But you did say something. I'm supposing that the structure here extends over W, but you can always do that. So that means the structure extends. So the geometric structure extends. Let's see. Yeah. So this has a geometric structure like a connection on a bundle. The bundle extends. The connection extends, and so on. So you take some extended structure. Okay, so this is the definition of K character. So it's a numerical quantity that you compute. And you don't need this W if you use this theorem, because this is an integer. This is what I'm saying it's equal to, but this is also equal to that. So you could actually sort of say that this number, when this bounds, is given as the 8 invariant of the boundary. Okay. All right, so this is a little more complicated definition than a cycle that Jim gave yesterday. But the statement is that you can put K characters here. So the set of K characters, these functions over X, is isomorphic to K hat, to structured bundles. So that's the main theorem, okay? And now all these maps are quite non-trivial. Well, you have to get the isomorphism. Let's see, there's a replacement for this one. This is K upper odd. Yeah, this is another thing. I give tribute to the Russian mathematics, since we toasted that last night at the dinner. This is a special axe I like to grind. Pontryagin duality says ordinary homology with coefficients in some locally compact abelian group is cohomology with coefficients in the Pontryagin dual group, and the Pontryagin dual, so the Pontryagin dual of homology with coefficients in some locally compact group, like the integers or something, is actually the cohomology with coefficients in the Pontryagin dual group. Now, in Princeton, which is the center of topology, you don't learn this theorem. You learn things like, here's an example. Take G to be a finite group, you know, Z mod 16. Then the Pontryagin dual is Z mod 16. And so this gives you the fact that homology with coefficients in Z mod 16 is dual to cohomology. They're Pontryagin dual. In Princeton, you learn with field coefficients, they're dual. But Z mod 16 is not a field. Z mod 2 is a field. And I was struggling with these Z mod 8 classes, and I said, what is a Z mod 8 cohomology class? And so anyway, from Pontryagin duality, you get it. And it turns out, miraculously, the same thing is true with K-theory. So it turns out you can prove complex K-theory satisfies Pontryagin duality. And now this, this functor here is given by this functor. And remember I said you could take coefficients when you have a homology theory. So so you jam all of that into this business to get this map into K-theory. So this is really the group that appears here is HOM. Now I'm going to switch from C to R. So I want to, I'm going to work with unitary connections. And there's a T singular version here, the R. And then this is HOM of something into R mod Z. So I replace C mod Z by R mod Z. Okay? And this something here is this, let me call this functor here. I put a bar, which means I collapse by these relations here. But this is also related to K-theory. So this is HOM Bordism bar with Z coefficients in the R mod Z. So Pontryagin duality says, if you put the integers here, you get the circle here. The Pontryagin dual of the integers is the circle. Pontryagin dual of the circle is the integers, right? So when you put integers here and take HOM into the circle, Pontryagin dual means HOM into the circle. This is G hat means this. So we're using Pontryagin duality, which is true for homology, that's classical, and in the 60s we found out that it was also true for complex K-theory. And then that's how you actually that's how you prove this theorem that this is a sufficient condition. You use this Pontryagin duality for K-theory, which we used in surgery theory to calculate the classifying space for surgery theory. Anyway, so this, by Pontryagin duality for K-theory, I can replace the K-theory with coefficients in R mod Z by the Pontryagin dual thing, which is the homology. So I could put that there. And then these are the K characters. So the K characters are functions from cycles into R mod Z. And then this map here is you take the form which gives you the variation. So given any K character, you're supposed to have a form, so you integrate this to get the value when it's a boundary. That's this map here. And now you see it goes into those forms, and I'm supposing it goes into those forms that satisfy the integrality theorem. And then that means that this will be well defined. All right, the integrality theorem is all you need for this to be well defined. I should say, there's something implicit in this, is that if you took another thing, W prime, if this is going to be true, then that means the integral of this plus the integral of this should be an integer. Because the integral here is equal to this fraction, and the integral here is equal to this fraction, so the sum of the two has to be an integer. So you have to be in this integrality situation. And so I'm replacing this, the GL thing here, by the thing that satisfied the integrality conditions. I should call them the Adams, Bott, Milnor, but now just it's easier, since new generation has heard of the Atiyah-Singer index theorem and doesn't know about Adams, Bott, Milnor. We'll call it the Atiyah-Singer index theorem conditions, okay? Everyone's heard of the Atiyah-Singer index theorem.
Yeah, but it's not so honest, perhaps.
What?
It is easier, but it is not maybe so honest. Sorry for that.
In this country, you worry about that? No, but it's also, I would say, no, it's also correct because, see, the meaning of the integrality theorem, see, that's what Singer said. What does this integrality theorem mean? It must mean there's an operator. So the meaning of the theorem is the Atiyah-Singer index theorem. Okay, so it's okay to call it that. So I'm slowly changing the diagram. First I put in k characters, and I sort of said this is an isomorphism, but the proof involves sort of substituting in and invoking these theorems. So I substitute in for GL the Atiyah-Singer conditions, because that'll be defined then, but they're the same because of this wonderful Pontryagin duality. And then Pontryagin duality here means I can replace this curious thing with R mod Z by this Hom, by Pontryagin duality, by Hom of the homology into R mod Z. And then this is just still ordinary. All of this is ordinary. And that's it. That's it. That's it. Those are the ideas. So the integrality, this amazing fact of Connor Floyd that this is a homology theory, the fact that Pontryagin duality holds for K theory, and then you can get a new diagram here, and then you get a new diagram where this is K characters, but this is the same as before, this is the same as before, and this is the same as before, and so by the 5 lemma, this is the same as before. Right? Everything, if I make sense of all this, I'm done. And so now we have a second, we're sort of, it's like Pontryagin duality for K characters. It's saying you take Hom of certain cycles into R mod Z, and that gives you the differential K theory, which is defined by vector bundles with connection. So what it means geometrically is there's a set of numerical invariants. If you have a bundle with connection, then, and another bundle with connection over the same space, are they equivalent up to adding trivial bundles and the trivial connection? Are they isomorphic bundles so that the connections, when you move them over, are Chern-Simons equivalent, same structured bundles? That's if and only if you compute all these numbers. You map odd manifolds into the base, compute these numbers, and they should be the same. So it's a set of numerical invariants that tells you when two elements here are the same. So there's things you can compute. And then this also gives a set of numerical invariants for K theory. See, the characteristic classes, even the integral ones, do not determine a vector bundle. But you can use these numerical invariants to rig up some rational invariants for here. I won't go into that now because of time, but it's just a little manipulation with manifolds, manifold boundary, and you can rig up a bunch of numerical invariants for elements in K theory, and they're Bordism invariants. And that's really how you prove this Pontryagin duality. So, see, Pontryagin duality says that when you have a cohomology class, it's equal to the Pontryagin dual of some homologies. That means it's Hom into R mod Z. And now I'm going to take R mod Z contains Q mod Z, which is the direct limit of the Z mod n's. So what you do is you construct a bunch of mod n invariants here, numerical invariants that determine that. Now this was already known in the 60s, but this gives a new proof of it. In fact, you have to give a new proof of this compatible with this discussion to prove this theorem till you have the 5 lemma. Okay, so you can sort of summarize this by saying this second part is I'm asserting that differential K theory, which is defined by vector bundles with connection, has a Pontryagin dual description as Hom of a bunch of cycles into R mod Z. And then, oh yeah, right, so I shouldn't. Right. So I could stop.
Sorry.
5 minutes? Should I stop? 5 minutes or stop?
5 minutes.
All right, fine. All right. Right, so actually we did this, we started doing this about 3 or 4 years ago. How many years ago?
Maybe.
5, yeah. So we got this far about 3 years ago, I guess. And then the next part is caused a 2-year delay. And you were supposed to mention that in your talk, but you didn't get around to it. Or you could have mentioned it. But anyway, so this problem, so the idea is to get a family's index theorem. So suppose you have a family, S, and on the fiber you have like, you know, complex manifolds. These are even dimensional manifolds. Even dimensional, say, complex manifolds or almost complex manifolds. Then, see, if you have this odd thing in the base with structure on which you can compute this numerical invariant that determines this guy, you could take the pre-image here and consider the thing over it. You consider this family over this thing, right? And this is again an odd manifold. And so you have a map from odd structured cycles here to odd structured cycles here. Although I should be a little more careful, I need to have a spin C, I need to have this additional geometric structure. So you have to have a connection on the bundle, so it should be a Riemannian submersion, and there's something about spin C, which I won't have time to talk about. Spin C is what you need to define the operator in order to define this integer in terms of an operator. That's all I'll say about that. But anyway, there's a natural map this way on cycles. Just take the pre-image. Odd cycles with odd cycles. So then there's a natural map this way on characters. They're functions on cycles. But that's the same as differential K-theory. So there's a wrong way map from differential K-theory here to differential K-theory here. That's called the push forward or push down. So we got a wrong way map. And then the family's index theorem in ordinary K-theory is an analytic computation of that push down. That's the family's index theorem. So you want to have an analytic computation. And I believe Fried and Greg Moore and people like that want to construct some, I don't know what it is, it's something called self-dual quantum field theory or something. And they actually want something even slightly more precise than this. But let's say for now we're going to do that. They not only want the structured bundle, but they want the actual bundle and the actual connection. I don't know, in a push-down situation. Now, I should say, the other people working on this are several teams. They do something different than what I'm going to describe quickly now. They actually look at each point, they look at the fiber, and they look at the L2 space of spinners on the fiber, and then they do take the Dirac operator, and then as the point varies, they get an element in K-theory, and they actually get a connection, and that's their pushdown. But then it's extremely complicated. There's a paper by Fried and Lott. This is going to be a sort of a poor man's approach. So we're not going to localize down to points. We're going to localize down to all the probing cycles, which are enough to determine the object. So we have this map on cycles. We have this map down like this.
Eventually, do you have eventually a nice theory of pushovers?
Huh?
A nice theory of pushovers.
What?
Of
A nice
pushovers.
theory.
A nice what of?
Theory of pushovers.
Yeah.
Pushdown.
I don't know what it means to have a nice theory. I have a definition of a pushdown. It's completely natural. So.
Does it consistent with composition?
Composition of what?
I think he's saying this is a nice
bundles.
theory of push-down.
No, he's asking. I don't know the meaning of your question, but I bet I could prove whatever property I could understand in a couple of years, maybe.
Okay.
Because this is extremely, this is so natural. It's just, you want to get a cycle here, I want to get a cycle here, I just take the pre-image, okay? And so then you get, by Pontryagin duality, Hom and Darman-Z, you get a push-down map in differential K-theory, and now we want to compute it analytically. So for 2 years, we were struggling or more with the fact that these fibrations are not so trivial. Riemannian fibrations. You've got several connections here. First of all, if you have a Riemannian connection here, you can pull it up and get a natural connection on the horizontal subspace. And then if you give yourself the Riemannian connection on the fibers are all Riemannian too, so you have Riemannian connection. And you can take the direct sum connection. That's one connection you can take. And it turns out the push down, when you look at the geometric structure, you have it here, and you do it here, and you want to actually prove this is a well-defined map on k characters. It turns out you've got to get this product formula, and so you're forced to you're forced to endow this cycle with the direct sum connection to make the product formula work. And then you get a push down. So I'm sort of cheating. At first sight, it looks like it's obvious, but when you structure this thing to get the product formula, you have to use the direct sum connection. Now, the Atiyah-Patodi-Singer theorem uses the Riemannian connection, or Bismuth made some generalizations to large connections with non-zero torsion, but the product connection does not satisfy those Bismuth conditions. So we worried about that for about a year. And so then it turns out there's this wonderful thing that the physicists told to the mathematicians, and I think the mathematicians like Chigger and Bismuth had been using it for a long time, and eventually some of that knowledge trickled down to us. And then Jim finally made a certain computation, which I'll mention in a minute, and then everything works beautifully. So let me just state what happened. So there's something called the, well, you can do the following thing. You want to use, you're forced to use the direct sum connection, but you would like to use the Riemannian connection up here. See, there's a natural Riemannian metric. You have the Riemannian metric here, the Riemannian metric on the fiber. You take the direct sum Riemannian metric, make it orthogonal. But the Levi-Civita connection is not the direct sum of the two connections. There's a difference, there's a twisting. But it turns out that it would be great if the Riemannian connection were Chern-Simons equivalent to the direct sum connection. But it's not. If it were, then I could proceed happily, but it's not. But it turns out you can do one of two things. You make the fiber extremely short, or you make the base extremely long and keep the fiber fixed. You do either one. These are scale equivalent. The Levi-Civita connection is scale invariant. If you multiply the metric by 1,000, it's the same connection. You don't change the connection. So, if you start scaling here, you don't change the Levi-Civita connection here. And then you look at this, and you look at the Riemannian connection up here as the base goes to infinity. It turns out there is a limiting connection. It's not a doesn't preserve the metric, but there's a limiting connection. And it turns out the limiting connection, the limit connection, is Chern-Simons equivalent to the direct sum connection, which we use in the definition of push forward. So that means you've got a theorem. This is the family's index theorem for differential K theory. So this is why we've had this delay. We started this 4 or 5 years ago, and kind of, I guess about in the last year we've understood how to finish this. So we get a family's index theorem is that the K character or differential K theory pushdown is computed analytically So this object is determined by these numerical invariants. So we take one cycle, we push it down, we take one cycle and here we want to compute this number. So this number is, we take the preimage up here, we have these, the push down is computed with this connection on the preimage. But we could also use the limit of the Riemannian connections by this is called the adiabatic limit. And so each one of these, because of the Atiyah-Patodi-Singer theorem, because of this property, we can compute all the values in terms of things that bound. There's a little detail here which I'm skipping, but that's it. We can reduce the problem to things that bound, and then this is given by this differential geometric term by definition because of the property. But then this is defined differential geometrically with the direct sum connection as a geometric structure. But by this Chern-Simons equivalent, we can replace the direct sum connection by the limit of the Riemannian connections. With the Riemannian connection, we have the Atiyah-Patodi-Singer theorem, which says up to an integer, it's equal to this eta invariant. And so we can write that is computed analytically as the limit of eta of the object of the cycle pulled up, endowed with its Riemannian connection, as we take the adiabatic limit. So that's a theorem that says something defined differential geometrically or kind of topologically can be computed analytically. And that's the way one could think of the family's index theorem. So that's an analytic calculation of the pushdown. So that's the end.
Okay, thank you very much. Actually, Dennis and Jim are leaving today, so let's thank them for beautiful lectures.
Thank you. So I've been planning how to make my wife not jealous. Everybody wanted to come here, so I'm going to say St. Petersburg is as charming as Amsterdam, which he was at recently, because it has all these canals and nice building, and as serious and interesting as New York, which is not charming. But Jim doesn't like me to say that. So thank you for inviting me. I've never been here before. Yeah.